Hello again, everyone. Today's video is going to be talking about the fundamental theorem of algebra as well as graphing polynomial functions in standard form. So before we go through actually defining what is the fundamental theorem of algebra, we're going to be looking at first what's the relationship between the number of zeros of a function and the degree of the polynomial. All right, so let's take a look at our most basic function first. First function you guys ever learned about was y equals x, a linear function, which is a degree 1 polynomial. And if we take a look at any linear function, we see that it crosses the x-intercept at one point, or the x-axis, excuse me, at one point. What if we looked at a degree 2 polynomial, a quadratic? Majority of the time we get some sort of a U shape like this that happens to cross the x-axis at 2 points. What about a degree 3 polynomial, a cubic? Right? If we take a look at this function, we get some sort of shape like this where we can have 3 x-intercepts. So, is this always the case? No, you're right. Think back to a quadratic. We talked about the discriminant of a quadratic, the piece underneath the radical in the quadratic formula, that b squared minus 4ac. We've talked about that depending on the value of that discriminant, you can have 2 real roots, 1 real root, or no real roots. In which case, if you have no real roots, that means that you have a pair of complex conjugates. I think you guys know where I'm going with this. Those imaginary numbers that we love so much, they're all coming back. And that plays into our fundamental theorem of algebra. So in our fundamental theorem, it's really talking about the degree of the polynomial is the maximum number of real roots that our function is going to have. In addition to that, it tells us that we have complex numbers that can come into play here, but when they come into play, they'll come into play as conjugates. So if we have, say, a degree 3 polynomial, let's say I redraw one, it could look something like this. In which case we would have 1 real root, and then this little wiggle spot over here is going to represent a pair of complex conjugates, right? We don't know what these are yet in this one example, but we'll go through some today where we'll take a look at how we can represent some complex roots. All right, so that is our basics for fundamental theorem of algebra, the fact that the degree of the polynomial is the maximum number of real roots of that polynomial, and that we have complex numbers that can also add into the degree of the polynomial. Again, the sum's got to be the degree. The number of zeros plus the complex ones has to be equal to the degree. All right, so let's take that new piece of information, add it into everything that we've been going over. For the last couple of weeks now, we've been looking at a lot of different theorems. We've looked at our rational root theorem, our factor theorem, our remainder theorem. We've looked at so many different theorems. We've talked about end behaviors, multiplicities. We've thrown out all this new vocabulary, and it's all so that we can have this piece of our unit right here, just so that we can sketch a polynomial function in standard form. All right, we see our first example up there. I kind of gave you guys like a little to-do list over to the side and some reminders. So the first thing we're going to need to do is to determine any possible rational roots. And for that, we're going to use our rational root theorem. So rational root theorem, we're looking at all of the factors of the constant term. So 1, 2, 3, 4, 6, 12, divided by all of the factors of the leading coefficient. Here it happens to be 1. All right, so we have 12 different numbers that we have to test. Yep, we got to test all 12 numbers. So let's go through. I'll choose the calculator to kind of help out, speed up the process a smidge. For that, I'm going to still use my store feature. So if I store 1 first as my x, and then type in my function, plus 3x squared minus 4x minus 12. All right, so is 1 a factor? Doesn't appear to be. The remainder is negative 12. What about negative 1? If I store that as x and then pop back up so I don't have to retype. Nope, looks like negative 1's not a factor either. The remainder there is negative 6. All right, well, what about 2? Go back to our function. 2, hey, looks like we got a winner right there. 2 is going to be one of our roots. So let's take a look at that root then. And I'm going to choose to use synthetic division here to help me. 3, -4, -12. Let's use our remainder theorem. So sorry, wow. Let's do some synthetic substitution. Bring down the 1. 1 times 2 is 2. Add for 5, multiply for 10, add to 6, multiply to 12, 0, just like we thought we would. All right, let's throw our variables back in here. So this looks like it's an x squared plus 5x plus 6. So if we were going to start graphing, trying to rewrite the equation for this polynomial right now, we know that this 2 over here, that root is an x minus 2 factor. And then we can take this information here as our second factor. And now, is that quadratic trinomial factorable? You betcha. So if we go ahead and factor it, we see that this is an example here of a cubic polynomial that has 3 real roots. So if we sketch out our little graph here, I know I have a root at, let's see, we're going to have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Let's say we're going to have a root at positive 2. So it's going to be an x equals 2 at negative 2. And at x equals negative 3. We are looking at a positive third degree polynomial. Therefore, our end behavior, we're starting out in this negative direction here. And as x approaches positive infinity, our function is also going to be approaching positive infinity. Looks like the multiplicity of each of these factors here is 1, which is going to equate to a cross for each one. So let me start in this negative direction here. I'm going to cross, 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 and in that positive direction. The last piece of the puzzle is that we have to put our y-intercept in here. If we go back, we are looking at standard form. Recall that your last term, your constant term, is also your y-intercept. We'll add that to our graph, and you just graphed your very first function in standard form. Very proud of you. Give yourself a pat on the back right there. All right, let's go down now and let's look at another example. So we have another graph function here that we need to graph. So again, let's go ahead and use our rational root theorem. Not a lot of stuff to test here, right? 1, 2, 4. All right, it looks like 6 options altogether. So that's good. Not a lot to test. Let me clear out what I had before for my calculator. And let's try to rewrite. Let's see. There's my function. So let's see. If I want to store, let's store 1 first. 1 store x equals now x cubed minus x squared, squared, plus 4x minus 4, enter. Hey, good job. I love it when I find 1, right? It gives me 1 quick, easy root. So 1 is a factor. So again, I'm going to go through and do some synthetic division. -1, 4, -4. All right, bring down the 1, multiply, add, multiply, add, multiply, add. All right, so far so good. If I try to rewrite this polynomial, I think I called it f of x. Yep. If I try to rewrite this polynomial here in factored form, I get that this root here is a factor of x minus 1. And if I look here, it looks like that's my x squared, that's my x, and that's my constant. So I don't need to write the linear term, obviously. I just get x squared plus 4. And now, is that factorable? No. Don't fall for the trick. Remember, we have a way of factoring a difference of squares, but there is no way to factor a sum of squares. So what does that mean for us? Since that is not factorable, we can try to just solve right then and there for that root, right? We know that the root here, we already said, was 1. If we try to solve this one, though, we would subtract 4 from both sides, but then we would go to take the square root of a negative number. So plus or minus the square root of negative 4 is the same thing as saying plus or minus 2i. So we do have 3 roots to this polynomial, as we would expect since we're looking at a trinomial, as we're looking at a cubic. We have 3 terms, factors. It's just that 1 is real and 2 are complex. So when we go to graph this polynomial, I'm going to have, change this, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. I know, again, it's a positive leading coefficient. I know it's an odd degree, so I know my end behavior as x approaches negative infinity, f of x approaches negative infinity. As x approaches positive infinity, f of x also approaches positive infinity. I know I can graph my one real root that we talked about at 1. And then from there, we have some sort of curvature to our graph outside of those roots that we'll just have to account for. What is our y-intercept here? It looks like it's negative 4. So I'll make sure I get that plotted on there. So that's 0, negative 4. So my graph, like I said, starts in the negative direction. I do have to cross here, right? Because the multiplicity is 1. So that's going to equate to a cross. And then as the graph's going up, it's going to have some sort of a dip and then pop right back up. Okay. The fact that the graph dips a little bit is what symbolizes these complex roots right here. All right. So a lot of information. Go ahead and rewind if you need to. Stop, pause, whatever you need. Go right ahead. Most importantly, if you got any questions, you know how to reach me.